Hello and welcome to our talk about Ceph at Proton. My name is Ján Senko, and this is my colleague Luis Domingues.
Hello.
We are representing a company called Proton, known mostly for our Proton mail service that I guess many of you know and some of you even use. Proton is a company based in Geneva, so we are very local to this location, to CERN and the Swiss Ceph community. In this talk, we will take you on a path through the past 6 years of Proton and how we jumped on the Ceph
World.
Yeah. All right. So, yeah, we will explain about the history of storage at Proton. We will talk about some of our solutions to certain problems and where we stand and what are our pressing matters. So, as for history, so when I joined this tiny startup in Geneva in 2018, we had Proton Mail. It was a mail service. There were beginnings of a VPN service and calendar. And we had a nice 5 million users, which is, for many companies, it's nice. And all the storage that Proton had was about 100 terabyte. Now, seeing some other talks, talking with some of you, 100 terabytes is nothing in today's matter. And back then, all this storage was stored in pretty standard MySQL. As many other companies store data in relational databases because it's the easiest thing to do. We were storing data in master, into replicas, on hardware RAID, with backups in some other servers. And we had a total overhead of about 10x. So for every megabyte that user stored, we had to pay for 10 megabytes of storage. And as Proton, as every other startup, was hungry for growth, we knew that this is not the way to go forward, and we started to look for a good scalable solution before this expensive storage would be too expensive. So we started to look for several solutions. I'm not going to name them now. But eventually, Ceph was the winner of our choice, and I specifically want to thank people from CERN and Dan mostly for some initial consultations, also Vido for consultations, and we have picked Ceph. So back then, in 2018, with this about 300 terabyte of storage, we started with our first Ceph cluster. So we were using Luminous in the beginning for proof of concept. By the time we got to production, Nautilus was just freshly out. So we started using that for production. And our first cluster was super simple. 8 one-use servers, each with 12 spinning disks. Again, I repeat, cost was the pressing motivation. And this gave us a nice petabyte of raw capacity. It was a cool petabyte. For people who never dealt with storage, petabyte is a very nice word. And that was the first thing that we had. We started with erasure coding, 4+2. 4+2 was mostly forced because we had 8 servers, so you cannot go to anything higher. So we were using 4+2 profile. And we had 2 data centers, and therefore we had mirroring between the 2 clusters. These two facts together mean that we had a 3x overhead, because every single cluster with EC 4+2 had 50% overhead, but we had 2 copies of each data. Therefore, every user megabyte, we had to pay for 3 megabytes of storage. This was significantly better than the original MySQL solution. 3 versus 10. Now, to store the data itself, we used a very low-level storage, and we used purely Brados, because all our backend that is storing the user data was already translating the user emails, user attachments through various levels into objects. So it was very easy to plug in Rados and store it at Ceph. So that was the beginning. And we started migrating our user data, and then we encountered our first problems. Or as we call it, small objects problem. So as an email company, well, mostly people stored emails back then. And the emails, they have these tiny headers, then they have contents, and sometimes they have attachments. Attachments are nice, they are big, but headers are very small. So we had plenty of objects that were just few kilobytes in size. And as we learned, as we translated our user data into Ceph, this was taking a lot of space in Ceph because of allocation units in Ceph. The default allocation size, I think, was 64 kilobytes, then it went lower to 16. But with erasure coding 4+2, every single email header was taking 400 kilobytes almost, which is 200x overhead, which is not great. Luckily, the average is out with the attachments that are good, but it still wasn't bringing us the benefits we expected from Ceph. But that could be tolerated. Okay, so maybe we didn't save as much money as we wanted, but it was still good. The second problem that we encountered was the recovery of the cluster. Right? You lose a disk, you lose the server. Okay, back then we didn't lose too many servers, we had just 8, but we were losing disks. And now, when we lost the disk, the others had to backfill, and all of these tiny objects had to be copied from other OSDs to other OSDs. And this process quite surprised us back then, because we didn't have the experience, and it took an extremely long time, right? Because the servers, the spinning disk is relatively fast, but if it has to seek after every 2 kilobytes to a new sector, then everything, all the speed estimates go out of the window. So therefore, we were pretty badly surprised that, oh, we lost the disk. What? It's going to take 2 weeks to recover from losing a disk? Our first solution was simply that we started ignoring the small objects. We did not copy the small objects from database to Ceph, and we just copied all the attachments and all the large objects. And by large, we defined 64 kilobytes and above. So we copied all of this, or moved, deleted from database, and this was a very good solution because we shrunk our database by 90%. So practically 90% of the data didn't need to be in the database and was suddenly in Ceph, which was much cheaper. Well, we still had the small objects. And Proton started to grow. We started to offer more services. And one of the biggest services here is Proton Drive. Proton Drive allows user to store any data, not just emails. And people love to store gigabytes or terabytes of information. And therefore, we knew we are in for a ride, and our storage started growing at an exponential rate. So we started thinking, how do we solve this? How can we put even more data in Ceph? We started looking at SSDs for the small headers for these emails, but it wasn't very feasible. Price was more expensive for SSDs, and the recovery problem wasn't still solved. Even on SSDs was pretty slow. So as we were working with very low solution, we implemented a very low-level solution. We called it multi-blob. So our objects, we call them blob from the database lingo. And multi-blob is just a concatenation of several small objects. You can concatenate these kilobyte headers into a larger file, which you can then store on Ceph. The objects in our storage layer, they are immutable. They are not being deleted that often. So we say, all right, multi-blob, when it's getting created, we put all these emails together and store it as a single object in Ceph. We found Rado's append, which we started to use for appending to existing objects. We had an extra logic which made sure that we are not touching the same object at the same millisecond with two appends, so that everything was atomic. And our target size for object was just 4 megabytes in Ceph. The moment the object reached 4 megabytes, we stopped writing to it, and then it was forever read-only. This was great, because from that moment, Ceph could backfill this object, can move it. If a disk died, the object can be moved very quickly, very efficiently to others. So Ceph had no idea we have small objects. So that was pretty good. Well, it has disadvantages that on top of our very elegant implementation we had in the beginning, we had this extra logic to handle this concurrency. And what was slightly worse is that now we needed to know extra metadata, like where is this object actually written? Because now we needed to know the name of the multi-blob and the index in the multi-blob. Right? So this extra information needed to be stored. But hey, we are already storing a lot of metadata for every object. However, this was special in Ceph. As I said, we had multiple Ceph clusters, and these tiny objects can be written differently in each data center, right? So in one data center, it can be in this object at the beginning. In here, it can be somewhere else. So these metadata need to be local to the Ceph cluster. It cannot live in our global metadata. So back then, we found out that Ceph has this fantastic feature called OMAP. I think back then it was for the first time when OMAP was like, the public API was really published, that, yeah, Ceph offers you OMAP data. You can put your stuff there. And practically nobody was using it, which should be a first signal. So we decided to write this data in OMAP. And how do you write this? So you need to have objects in Ceph, but we didn't want to attach OMAP data to objects, because the OMAP data is there to help you to find where the object lives. So we created these anchor objects that are 0 byte in size. It is similar to, I think, Rado's gateway. OK, anyway. So these anchor objects of 0 byte size, and information for every single tiny object was attached into OMAP to one of these anchors. So as we were writing all the millions or billions of small objects, the information was written into OMAP. Now, here I say, in the slide, you can see that we had about 10 billion small objects written in our cluster. Our cluster was mixed. We had large objects, we had small objects. Now, for this small object, so we had about 150,000 OMAP entries in every anchor. So our OMAP pool was extremely large. And around that time, we found out that we are probably the largest users of OMAP. Or at least when I was talking at the previous Cephalocons, I didn't hear anybody having similar experience. And it wasn't that great, because quickly we found out that it wasn't performing as well. Well, when everything was good, this was performing fantastically. Reads and writes, latency were great. However, we had problems, again, with backfills and outages. All these anchors that I mentioned, these fake objects, were constantly updated. All the OMAP data was constantly appended to them. And even if a single OSD went offline, even for a minute or for a few seconds, when it came back to the cluster, all these updates to OMAP were treated as like, oh, I need to download this object from scratch because you appended a single value to it. So the object was big, it had 1 million OMAP entries, and the magnitude of the backfills, or how much data was exchanged between OSDs, was extreme. So that wasn't very great, but we also didn't have too many ways because we were constantly updating every single object. We also found out a second problem, the tombstones in RocksDB, and previously our colleagues were talking, we had a very nice talk about tombstones in RocksDB, and we found we also hit a similar problem when we were backfilling, when we were moving data from one node to another. It went fine, but at the last moment, when the original OSD got emptied, that node started compacting and stopped communicating with the world for several minutes, which wasn't great for our users. Luckily, we had a second cluster to fall to. But yeah, these were some massive slow ops that were constantly happening when you try to drain a node or something similar. So that was our first OMAP solution. And then we were thinking about how to actually make it into something nicely working. And we got our second solution, that instead of reusing the same anchor objects all the time for eternity, every day we create 1,000 new ones. And all the objects, all the data that is written in that day are attached as OMAP to these anchors. And when the day is over, we create 1,000 new ones, and the old ones are read-only. So they don't change. So in our cluster, we have 1,000 objects that are constantly getting appended, and everything else is just chilling. So when we have a backfill, when we have any operations, this data is pretty stable, and it's not the cluster is not throwing a fit. So the changes are much smaller, and it's performing again very well. The tombstone problem is still a problem, mostly because of the legacy data that still exists, because we don't want to touch it because it causes an outage. So we usually upmap everything in place in there. So in our SSD pool that contains these OMAP data, we are using upmap a lot to make the data stay where it is and not trigger any tombstone bugs. And slowly we are compacting some OSDs. All right. So now I'll give word to my colleague Luis, who will tell us about some nitty-gritty details.
I will go through the history of deployment tools we use at Proton. So I saw a lot of some talks, and I talked with some people that they use one tool and they have a long history with it. And at Proton, we are quite the opposite. We use everything. So we started with Sensible. I will go into details after for each tools. But basically, we started with Sensible, so 2 clusters for the user data. We have 2 clusters for internal use that we use for RBD, S3, and just internal services that need storage. And we have a third cluster that was deployed this year with Reef. I will go into details. So we started with Ceph-Ansible. When we started using it, the clusters were quite small, and we liked the idea of having one Git repository where you have everything inside. You know, Ceph configuration, the configuration for the OSDs, for the daemons, the configuration for the deployment. You just do a merge request. You ask your colleague to approve it. He approves it. You merge into master or main or whatever the name of your main branch is. And you have a pipeline that runs and pushes everything to your cluster, and you have your configuration change. It was nice when the cluster were small. Now we have more than 100 nodes with more than 3,000 OSDs per node, per cluster, and yeah, doesn't scale very well. We have pipelines running for 80 minutes, so basically you just do a change that should not change a lot, like mclock profile, for example. You ping your colleague to review the merge request, and then you go to launch because it will take forever. So yeah, we started to look into other solutions because Ceph-Ansible will be phased out so at some point, and because yeah, it wasn't very the best. So we had to choose between two solutions, Ceph-ADM and Rook. So we choose both, but on different contexts. So Ceph-ADM, we use it on our smaller internal clusters. We call it corporate clusters. So they are quite small. It's just for internal usage. We expose RBD. That's the main issue for Rook, because we need to route all the daemons through all the networking, all the infrastructure, because it's some Kubernetes clusters use it, other products can use it, so yeah. We cannot have the cluster that is isolated in some Kubernetes installation. And indeed, it was a lot easier. We started to separate the configuration of the deployment itself from the Ceph configuration into two different sets. But we still have some Ansible around it, because we don't want to have an inventory, for example, that is manually set up. So we have Ansible that will ask for Netbox to have all the nodes with labels and everything, and it will generate everything we need for the specifications for the nodes, push it to the monitors, and then apply the changes. And Ceph-ADM will take care of everything else, so deploying the daemons, deploying the OSDs and everything. But still, we have some Ansible around it to pilot it. And yeah, we try to have the GitOps approach, where everything is done via a Ceph repository, merge requests, for eyes reviews, and stuff. Our main clusters, however, they are isolated. As Janos explained, we are quite low level, so we have a tool that it's called Ceph Storage API. That's the entry point for the storage for all our products. And that is the HTTP endpoint that then talks to Rados. So we can have a cluster that is completely isolated, and we just expose some entry points we select. So for our new cluster for user data, we used Rook because why not? And because in the team, we start using Kubernetes more and more. So instead of having each tool having its own deployment setup, we use Kubernetes, and we standardize around it. And yeah, it makes our life quite easier. It's quite still new, so we still are learning to play with it. But for people who are afraid to try it, we don't observe any performance penalty. We use HDD, so I mean, it's probably our bottleneck anyway. And the Rook operator is quite feature complete, maybe not tiny, some border case configuration, but for most of the use we need, it's plenty. But if you just want to deploy a self cluster, you need to take care. If you want to go with Rook, you need to take care of the Kubernetes cluster with everything that goes around. So, yeah, I think both solutions are valid. Depends on the context you are using them. So yeah, that's it for our all deployments. So if we want to summarize Ceph at Proton, today we store 30 petabytes of user data in each cluster. We have 3 clusters. Objects are quite small, so we still have the multi-blob an OMAP issue that is still hanging around. We played a lot with mclock because of our pattern usage. It was a lot of try and fail and retry and change every possible setup you can find on the documentation and see how it behaves. That was for Pacific. It works a lot better out of the box with Riff. So yeah, kudos to the people who implemented the mclock. And yeah, we have our small clusters that are more self-compatible on their usage. And yeah, we see the behavior when we have rebalancing. They are a lot more easier to manage.
All right, so what is in active development? So yeah, some growing pains and some decisions maybe we regret now. So we started with 8 servers, now we have 120, but we are still we still have the original pool that we started back then because it has user data. We could only use Erasure profile 4+2. Obviously now with 120 servers, it would be better to use something better, because we also have 3,000 hard disks, and some of them are 6 years old. And you know what happens to hard disks when they are 6 years old? They have a very high failure rate. And oh my God, I learned so much about the failure rates of various vendors and over the past 6 years. So 4+2 is not safe at this scale. So even with 1% failure, which is just a golden target and not the worst case, we have about 12 days between the disk failures, right? And when it's a bad week, it's significantly less. And Erasure coded 4+2 gives you you can lose 1 disk, and when the moment you lose the second disk, it's a coin toss, right? Is it going to affect the same PG or not? Is cluster going to lock itself in, and not write anymore? Luckily, we didn't have a very bad situation, but yeah, it's making us nervous sometimes, especially in summer when data centers are hotter. So for new cluster, we started with 8+3 Erasure coding, and we will see about what we do to the existing clusters. For the small objects and multi-blobs, well, the OMAP SSD is growing. Now it's steady. It's not throwing slow ops, so that beast is tamed at this moment. But we are still very careful on rebalancing this pool, and we have some new solution in R&D stages, because we would like to replace it with something more stable. Yeah, and as was shown, we are reaching 100 petabytes approximately of raw storage. So that's only another 10x between the scary exabyte word, and we are looking forward to growing into that scale in the future, because Proton Drive and other projects are quite successfully growing, and yeah, it will be an interesting path. So once again, I want to thank the Ceph community, CERN, and all our friends that we've been talking during this talk. So we are available for questions anytime, but we still have 4 minutes until the next talk, so if anybody has something.
Thank you. Are you aware of the small object enhancements in erasure coding coming in Tentacle for kind of 4K sized objects?
Sorry?
Some enhancements in Tentacle for small objects, so 4K sized. You'll no longer write them to the... so on an 8+3, you'd write 4 times 4K for a 2K object.
So the small objects, we put it multi-blobs, right? So we don't have 4K objects in Ceph.
You don't anymore, no. Would you change your design if that were the implementation?
If it would it backfill efficiently?
Yes.
All right, that's a very interesting thought.
Okay, let's talk after. Yeah.
All right, gladly.
I'm curious about the Rook cluster. So did you already you actually mentioned the Kubernetes management that actually needs to be done at the side. So did you already actually also upgraded Kubernetes since you started, since you deployed the cluster with Rook?
So we didn't upgrade Kubernetes on the production cluster, but we have a test cluster where we did the upgrade from at least from the network components. So yeah, that's things that we are testing.
Because I understood correctly, like it's several hundreds nodes as well, that the Rook cluster that you deployed.
Mm-hmm. Yeah.
All right. Thank you again.